Recording in progress.
All right, so in this second part video, we are continuing our discussion of word embeddings, auto-encoders, and the relationship to BERT, the BERT transformer. So you can reference back that first video, part 1, to pick up. All right, so in the second video here, in the second half, today we are going to cover, we're going to dive into transformers, knowing what we know already about word embeddings and what we know about autoencoders from the previous one, and we're just going to pick up here. So in a previous lecture, I said this is the general architecture for a transformer. You've got your inputs here. They go into the encoder, which is actually made up of several layers. You get the encoder output, and then the encoder output is then added into the decoder plus another input. So the second input, so for the classic example of English sentences and Portuguese sentences, so you would put in the English sentence, encode it into a vector, and then that vector then becomes the input to the decoder, but also the Portuguese sentence. So both of those go through the layers, and then at the end, it's going to predict the next Portuguese word in the translation. However, so that's the generic 2017 Vaswani encoder decoder with multi-head attention architecture. Today's focus will be on the BERT transformer. In the BERT transformer, we are only going to focus on one half of the decoder. Okay, so here we're only going to focus on the encoder part. So really, it's like we're going to slice out this and we don't use the decoder. So really, we have inputs here, and then what we get is this. So I'm having a hard time writing on here. But what we get basically is the encoder output, okay? So that's our, the thing that we get from the architecture. So we only use one half of it, okay? Questions? Yeah, there we go. All right, so that's the basic idea, okay? So that's what we're gonna do. So I wanted to start there just to kind of emphasize that it's no longer the full encoder decoder architecture. BERT is actually just the encoder itself. So let's go over to the whiteboard then. All right, so now that we know that BERT is only, so now BERT, right, the BERT transformer. Okay, I should basically spell out BERT, I would assume. So BERT stands for what does BERT stand for? BERT is you would think that everywhere you have. You guys have that in front of you? Bidirectional encoder representation from transformers. So that's what it stands for. So BERT stands for bidirectional encoder representations from transformers. Okay, and notice that, you know, the keyword there, representations. Every time you hear that word in deep learning, basically you're talking about what? Embeddings, right? Some type of embeddings. BERT is just one gigantic and very smart embedding machine, right? That's kind of what you can do that you can say about it, and it is basically an encoder. Really, you have an architecture like this, where you have an input and then you have an encoded output, basically. Okay, something along those lines. And you have, remember, it's still a transformer inside, which basically means it's got attention, as we described in that previous video, and the other components, just no decoder. Okay, so let's go ahead then and talk a little bit about the architecture of BERT. So there's usually, whenever you're talking about transformers, there's going to be the what's called the BERT base, and then BERT large, right? And this applies to like Albert and Roberta and all those. So what this means basically is, I think whereas here you have, I'm going to say 12 encoding layers, this is 24. So there's more parameters for everything. The embeddings are bigger, you know, that kind of thing. Okay, so just keep that in mind. So usually the large will be better at predicting, but it's going to have a serious impact on your GPU performance. It's going to be slow. Okay, so that's one idea to kind of think about. Okay. All right, so this is you know, BERT like that. So now that we know that BERT is just the encoder, we're going to treat, you know, it's got all the encoding layers, right? If you refer back to that lecture that we did on transformers, an encoder layer has what? Has an attention layer followed by a feed forward fully connected layer, which is just a standard layer of a neural net, right? So all, you know, those are there. So that's the inner workings of it. And that's, you know, something that you guys know about. So if we go to the, you should be seeing the PDF document here. If we just find our original diagram, and keep in mind positional encoding is also included just like the transformer here, right? So this is the encoder layer. It's got an input and output. Notice that the dimensions are pretty much the same. Number of batches, that's the number of sentences that you give it. Number of tokens allowed per sentence. So notice that there's a limit. I think the limit for BERT is actually 512 and not 40. And then the embedding, right? So that just means the size of it. So they're pretty much the same. There's a multi-head attention, and then there's the fully connected layer, and we've talked about this already. So really, I'm going to skip the part about the inner workings of BERT, and then instead, we're going to focus really on the inputs and the outputs. Okay, so that's really what's kind of important to understand the differences of BERT. So let's take a look at the architecture of BERT and see how it trains. So if you remember, we said that encoders, auto-encoders, take an input of 784, let's say, MNIST, and it reproduces the same image, right? Kind of like that. Well, in BERT, we kind of do the same thing. We have an encoder here. We have an encoder, okay? And the encoder will have a set of tokens that it allows in. And that's usually capped, I think for BERT, for most models, at 512. The reason why it's not bigger is that if you remember, you're creating an attention matrix. And the attention matrix is actually 512 to 512 because you have all the words here and all the words here, and then you're paying attention. So it's like you're finding that this should be attention. This word and that word should have high attention. And then this word and that word should have high attention. So you create a matrix that is 512 by 512. So as you might imagine, if you gave this a whole document of 10,000 words, this would be a 10,000 by 10,000 matrix. And that is not something that we can handle with today's GPU power. So the attention mechanism is actually limited by this. So this is really rather important. Does that make sense, guys? Okay.
Yes.
All right, great. So this is then the architecture of BERT. It's going to be 512. So, and the outputs over here are going to be also 512. No magic there. Okay. And then all the layers. So like I said, we're going to treat everything inside as a black box because we've discussed it already in the Transformers lecture. So now we give inputs to BERT, and what we get out of it is embeddings. Encoded embeddings. This is what you get. So let me do this. You know, you get like embeddings. You see that? All the way to here. Now these embeddings, I'm just going to do this kind of to depict that they're vectors, but you set the dimension. So I think for BERT, the size is 768. That's the last layer, the last hidden layer basically of BERT. So there's 7 and 68. Okay, these are the embeddings that you're basically getting. So if you think about this in terms of a tensor, this would be batch size, which is the number of samples that you give it all at once, which are treated independently, and tokens, which is 512 in our case, and 768. And 768 here. $768, right? That's the dimension that you get. So for every sentence or every token that you give it, you get this batch size and tokens 768. So that's kind of the tensor that you get as an output given and the input is same thing, batch size and tokens that you provide, but they're not embedded at this time. They're just kind of like blank. All right, so now this is the architecture of BERT. 768 is the hidden size. So it's the last hidden layer of the neural net. And tokens, let's just say is 512. Okay, 512. All right, so those are kind of like the mechanics of it. Now, what is the input? Let's think a little bit about it. So here, this is the generic TensorFlow machine, and then from it, you can do lots of things. Okay. So the inputs are where it's kind of interesting. As it turns out, BERT provides a token. You know how there's special tokens that transformers use. In general, they use startup sentence, end of sentence. These can have other names, like end of sentence can be EOS as well, right? So, but they kind of have the same meaning. Now, you guys know already that there is a mask token because you've been playing with that. Well, now I'm saying there is a new one, CLS, right? This actually stands for class. So you can see where this is going. Could be a type of label. And there are other ones. There's a new one called Sep Separator. And that's when you want to give the transformer multiple sentences. So you use that separator tag in between two sentences and separate it out. That's kind of the idea of it. So here in this example, this is 1, 2, 3, all the way to 512, right? So in the first, we give it CLS, the class, then we give it the words. So for instance, help the princess ... right? So you want to do something like that. So this is your input. And then what you're going to say is, for a generic problem, notice that the first one, embedding, is the class. So really the last, so now when you look at over here at the output layer, you could say, well, we have 512 inputs, 512 outputs. So is it possible that for the word help, the embedding is this one? You see that? And then for the word the, then that's the embedding. For the last word, this is the embedding. But interestingly, then what is this embedding here? What is this one? Because all we say, it's that is a class embedding. So what are we using this one for? Well, this presents an opportunity with BERT to kind of train BERT according to individual classes to predict something. So it's almost like the idea would be, if you want each word to be represented as a vector 2, then you grab the 2. So this is 1, 2, 3, right? So I want the embedding for 3 input. I grab I grab this vector, the 3 vector. Do you guys see that? However, if I wanted one whole embedding of size 768 for the entire input, well, as it turns out, you could just grab this one, and you could argue that depending on how you train it, that this vector of size 768 represents everything. So you basically encoded the entire transformer input into that vector. Do you guys see what I'm saying? How does BERT know to do that? It knows that because for all the inputs that you are doing, you're always defining this first one as CLS. Every input that you give it, this is always CLS. So it's going to start to learn something about this generic vector that outputs here, that is, it has something to do with the class of the sentence. So it's almost like you're saying, well, that is the class of it, and you should encode it, basically, and figure it out. Does this make sense, guys? Questions? No questions? Okay. All right. So anyway, so the idea with BERT is like this. You know, now the architecture, if you notice, is not really changing. What is happening is what you do with the inputs and outputs is what's really important. Remember that you're giving it sentences. Help, the princess went to the forest, you know, something like that. The first one is the CLS. So you're saying, you know what? This is the sentence, but the first one should be a class, BERT. Figure it out. And then BERT starts to create this encoding, which it associates with a class for the given sentence. So that's the intuition with how BERT works initially. So let's take it a step further. So BERT is actually if you remember when we talked about transformers, we said that there's a phase 1 and a phase 2, right? And we usually said that phase 2 is either the fine tuning or the unsupervised use. Okay. However, in our example, we're not going to look right now at fine tuning. We're only concerned with phase 1. Phase 1 is pre-training. So how do we pre-train BERT? So BERT is actually pre-trained on 2 tasks. Okay, remember this is phase 1, not fine-tuning, but just the pre-training phase. But still, there's got to be some objective when you do this. So it's actually pre-trained on 2 tasks. One we can call the masked. One we can call the one we can call the masked language model. And the other one we can call the 2-sentence classification. So we've got the masked language model task, and we've got the 2-sentence classification. These were, by the way, the original 2 tasks on which BERT is trained in the pre-training phase 1. However, they've added more. They actually, I think, don't like the 2-sentence classification task when it's a current sentence and next sentence, and I think they've changed that now to like similarity or something like that. So these are that's why you get like, okay, Roberta does this instead of that. But initially though, the original BERT was pre-trained on 2 tasks, which were the masked language model task, which you probably can already figure out what that is, and then the 2-sentence classification task. Okay. Any questions so far? No? Wow, I must be a great explainer of things. You guys have no questions. All right. Josh, you want to say something now?
No, I was just taking it all in.
Taking it all in, too much absorbed. All right. So let's look at the first one, right? So let's take a look at the first one. So the masked language model okay, is the first task BERT is pre-trained on. Okay, so let's call it the first one. First pre-trained task. Okay, so this is why BERT can do the masking, because it was actually trained on this idea. Okay, so how does this one work? Well, we take the original architecture, right? This one, like that. And now we're going to add a little bit more to it. But we don't change the inside of it. We just kind of change the inputs and the outputs. So now we're going to model, this is a transformer. Remember, it's a BERT transformer, just the encoder phase of it, not the decoder. I'm just going to call it BERT. I made it long because it's just easier for me. So again, you know, does something like this, inputs all the way to the last one. Let's give it some numbers here. So we've got 1, 2, 3, 4, dot, 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 all the way to 512. That's the number of tokens. And then we've got the same set of outputs, remember? That's what's so nice about it. Okay. And the same set of numbers. 1, 2, 3, 4, 5, 12, just like that. So still the inputs kind of look the same. We've got the CLS tag here. And actually, no, hold on. I have to do something here. Now we're going to modify it a little bit, but not too much. And we're going to say mod input and then just plain input. So we still want to say that the first one is the class for it to pick up on that. Then we say, let's say, let's stick to improvisation in ... So I'm going to need one more token. Well, I'm going to need a token here, a token there. And then here, there would be something, or maybe at 512, it's probably padding. Okay. So we're going to say this is 5. And then this is 6. So then here, 5, 6. Okay. Now what we need to do is we're going to modify this a little bit. Use a different color. And now the input will be CLS, let's stick to in. But the word improvisation will be replaced with a mask. You see that? That's exactly what you do in the first pre-trained task of BERT. You mask it. And then what you want it to learn is you want it to predict this mask. Okay, that's the objective. So it's going to do an encoding here, just like the other ones, right? So it's going to have its encodings for the individual terms. And let's say of size 768, 768, 768, 768, 768, 768, 768, including the class one, which could be thought of as an encoding for the whole thing. But what we want the model to do is to predict this word. So it should predict the word improvisation. Why? Well, if you think about it, I'm going to have to erase this. So I need the space. So let me just put it up here. I'm going to say this is the mass language model. So now what you do, remember in the pre-training phase, I'm gonna change color here to blue. And what I want is I want it to predict that word. So that means that I'm gonna run it through another layer. Which is going to be a fully connected, feed-forward, fully connected neural net and softmax. And then this one leads into a vector of size vocabulary. Have you seen this before? Where did we just see this? Guys, where did we just see this? Here, right? We just saw it here. Same idea. We had a feed forward connected with softmax functions. All right, you can see that with the softmax function for a vector of size vocabulary size, and it gave us the word, right? So similar approach there. You can see how things build on top of other things. And so the model here will predict for the language model task, this is going to be the predicted word. Oh, predicted word. So it's gonna predict something, and we already know because of the input that it should be improvisation. You see that? So it should be improvisation, and it's gonna predict the word with a softmax probability, and that's how we know if it did it correctly or not, right? So we can measure the performance of the transformer given that we have we have the whole sentence. Let's stick to improvisation in randomly. I think what it does is it takes whatever text you give it, and randomly it takes 15% of it, and it's going to mask it. So what that means is it's going to take 15% of the words randomly, and it's going to replace them with a mask, but it knows what the input was, right? So when you get a word here, improvisation, remember also that it's going to be the one-hot encoded vector or the ID. So it'll be able to compare improvisation to the original one, and then know if that's how it learns, basically. Is there any question about this idea? Questions? Does it make sense?
Yeah.
Okay. All right. Good. Good. All right. So this is the pre-training phase, and this is how it learns. But as I said before, BERT actually learns, so that's masked. It also, there's another, is pre-trained on a second task, which is what's called the two-sentence classification task. Okay, so that's another way of training the weights. We're going to change the weights now on the second task. This is the two-sentence task in pre-training. Oops. In pre-training. So here, the second task BERT is pre-trained on is a two-sentence classification task. So now, again, we're going to take the architecture. Remember that inside, it's pretty much the same. It's just the outside where we need to think about it a little bit. So once again, we have an input, but this is for a different task. But it's also unsupervised in the sense that we have without labels. So here, once again, we have the tokens, right, all the way to 512. And that's what we need 512 because now we're going to try to fit 2 sentences in here. So I have my CLS, once again, and then I'm going to throw in the sentence, the man mask to the store. But there's a second sentence, so I need a special token to indicate the separation. So that's usually the separator task. If I didn't say this already, the CLS here means class, stands for class. And then here, you would put in a text, you would have, you know, the cat is sleeping, and then the cat went to the windowsill, right? You would have those 2 sentences, so the current and next sentence. However, you also want to train it with sentences that are not sequential, right? So those would be examples of bad things, of sentences that are non-sequential. So this is a 2-class problem in that sense, is that you have sentences that follow each other, and then randomly what you can do is just take one sentence and then find another sentence anywhere else in the text, right? They're not, I mean, it could be that coincidentally they would have followed each other, but most likely they're not. You see that? So for instance, in this example, penguin mask are, or penguins are, and then again, just to wrap it up, you would put another separation just to indicate that's the end of that sentence. So if you think about it, this is sentence A, let's say. And this here is sentence B. So sentence A is the man to the store. What do you think the mask would stand for here? Went, exactly. The next sentence says, penguins are. What do you think the mask could stand for here?
Birds.
Penguins, birds are? Maybe penguins who are, correct? Maybe who are, maybe.
Oh, I'm sorry, I read that wrong then, or heard it wrong.
Grammar kind of thing, right? The point is, we have a lot of text, 2.5 terabytes of text, right? So that's going to be helpful. Now, I ask you the following question. Are sentence A and sentence B, do you think they follow each other? Does sentence B follow sentence A? Or are these examples of sentences that are not next to each other?
They're not next to each other.
They're not next to each other. So this is this would be like a negative example, right? And then the man went to the store. The man and the man got some milk and, you know, diapers or something. So that's basically the an example of a positive case. And this is an example of a negative case, but notice this is unsupervised because this is in text already. So now what is the objective of the transformer in the 2-sentence task for pre-training? We're gonna go back to the architecture as we know it. And we're gonna say here, right? So in this task, the objective is not just to predict the mask like it was in the previous one. In the previous one, sorry, yeah, for the given mask, we know that it's improvisation. We want to predict improvisation, right? That was task 1, the mask language model for pre-training BERT. Now we're dealing with the 2-sentence task. So these are again 1, 2, 3, 1, 2, 3, and so on, right? If you remember, we have this thing called a CLS here, right? This CLS, because we have the CLS here, and then we've got this one over here. So we can use that actually in this task very nicely. All we have to do is, we don't even care about the embeddings of the words or the masks or anything, because our focus is this one. So what we can do is for this class, which is, because remember, all of it is connected, right? So it is learning basically. Remember that, neural nets are basically mapping machines. They map this to that, they map this to that. In this case, we're saying that the CLS is a special kind of thing. So it should map the entire input to this one. But we can actually make it supervised by just adding a layer, which is going to be a fully feed-forward, fully connected network plus softmax. So now we're going to have probabilities. And then here, we're going to have a simple vector of 2. And this vector, because we know, for instance, that these from the text that these were randomly picked, so they're not together. So their example of is not next. But if we grab 2 sentences that are together, we know they are next. So basically here, we can define a class is next versus not next. Do you see that? So in this case, in the training here, the model should learn to say what? The softmax should return high probability for not next and 1% probability for is next, because these are not next. The point is, when you pre-train BERT, initially you can pre-train it on the mass language problem of predicting the words, and also on predicting that 2 sentences are next to each other or not. And the original BERT transformer was built entirely on these 2 tasks or objectives. And believe it or not, giving it 2.5 terabytes of data or so, using the attention mechanism that I mentioned before, right? Attention over here. And everything we've said about transformers, the transformer can actually learn not just grammar, but semantics and everything else. And if you think about it, the outputs are still embeddings because they're just 768 vectors that we can use as embeddings. So now if we want to embed a word for the specific, we could use this vector of size 768. If we only have 1 sentence and we want to embed the entire sentence, how do you close this thing? This thing opens sometimes. Oh. You guys know how to close this thing?
Close what?
Yeah. Oh, you're not seeing. Okay, great. So that's the idea. Okay. So, and these are the embeddings that we can create. If we wanted to create a vector, let's say that you wanted let's say that you have, you know, a whole sentence, right? And you wanted just one embedding of size 768 for the whole sentence. What do you think you could do? What do you think? Let's say I have, let's stick to improvisation in, right? And the rest is padded. But I just want it, this gives me a vector of size 768 for each word, but I just want one vector of size 768 for the whole sentence. What do you think I could do?
Take the class.
Sure. Take the class, right? I said that actually, that the class should represent an embedding of the whole thing. That's true. You could also take the individual ones and average them. That's another way of doing it. But as you can see, BERT is just, what is BERT doing? It's taking inputs and producing outputs, right? Of a specific size. Without a fine-tuned task, they're pretty general. But if on top of this, we had done the named entity recognition or some other kind of fine-tuning, the vectors would be more specific to that task. Remember what I said, according to the literature, Word2Vec is still better, but for specific tasks, obviously, BERT is better, or these transformers are better. And then as far as how BERT is trained, as I said, it uses the masked language model of predicting, giving a mask the word, which you guys have already seen that applied, and then the two sentence to say if two sentences are next to each other or not. And that's it. That's as far as, that's everything I have for today about BERT. Are there any questions? Any questions, guys?
Not about this.
Not about, so all of this made sense to all of you?
I'm probably gonna watch the video another time or two.
Oh, okay. So is it too hard then? Is it?
No, it's just, I mean, we're sitting here for a few hours, so it's just taking a lot of information.
Okay, is it, yeah. All right. Well, I hope it makes sense. I mean,
Yeah,
yeah.
for the most part, it did. Like, I'll just rewatch it just to get a better understanding.
Okay, all right. One thing I can do is, let me save this as a PDF. I know I can do that. Yeah, so. And so now I think I've saved it here. So let me, this is BERT, right? So BERT whiteboard. Okay. And I'm going to put this on Brightspace so you guys have that as a reference, maybe. So I've not written a chapter on this yet, so unfortunately I don't have that. But I'll put these as a guide at least, and then take a look at the video. So let's go to the Brightspace. Okay, you should be seeing Brightspace. So here, I'm going to create a new module, word embeddings. Auto-encoders and BERT. Okay. And I'm going to load that PDF. All right, so there it is. So that should you open it, you'll see the general idea. So it's really these models that's what's important, just to remember what goes where. Okay. All right, good. All right, so we're running out of time. We have about 20 minutes. So let's see. So I don't want to rush you through the similarity code. So you want to hold off on that one until next class and just talk about the project now, or what do you guys
Sounds
think? Sounds good. Yeah. Yeah, I just don't want to rush through it. That will be the next topic though. So let me actually, at least for those of you that kind of want to take a look at it, we can do that. So let me share this screen. So the next topic was going to be the unsupervised part of BERT, right? So looking at in the fine tuning area, we saw last week that we can fine tune it to an annotated data set. But what if you don't have an annotated data set? Then you would need unsupervised techniques. So that would mean basically embedding things. So we use BERT to embed things, and then we try to perform some analysis. So if you look here under transfer learning, Hugging Face, I've added this directory, embedding sentence similarity. So I'm going to click on that, and you can see I've got embedding approaches for sentence similarity, which include GLOVE, which GLOVE is like a better word2vec. It's like, or basically it's like using word2vec, but on a very large general data set and using those embeddings. That's what that is. GRU just means it uses like an RNN to create the word embeddings. And then we have BERT, the plain vanilla BERT, and then we have something called SBERT, which is a better version of BERT for this. And then we have a fine-tuned Roberta for sequence classification, which is what I had talked about. So if we look at the code, you'll see it's not really that long, but I don't really want to rush through it today, given that we don't have that much time. So, but you can read through it. I think it's pretty similar, or it's pretty simple. And you know, you might be able to figure out on your own, but I'll cover this in the lecture next time we meet. Does that sound good? Yep. All right, great. So what we're going to do now is we have some time, a few minutes. So I'm going to stop the recording.